Hello, and welcome back to the Cedille Cast. In this video, we explore a pragmatic issue in using dependently typed languages, efficient reuse of data, programs, and proofs. When programming with dependent types, broadly there are two styles of giving proofs about programs. One style is extrinsic verification, where first a program is written, usually in a simpler fragment of the language, and then second, a proof is given concerning a property of that program. An example of this might be defining merge sort as a function over lists whose elements have some given ordering, then proving that the order of the elements as they occur in sorted lists respects the given ordering. The other style is intrinsic verification, wherein the properties you are assuming or guaranteeing are baked into your data structure, and the program satisfies the desired property by construction. For the merge sort example, this would correspond to having a bespoke sorted list of elements data type, and merge sort would take in any list of elements with an ordering and return this sorted list data type. There are merits to both approaches. Extrinsic verification is useful for one-off proofs of properties or properties hard to express as a data type invariant. Intrinsic verification is especially nice when combined with language facilities such as dependent pattern matching, which propagates the equations implied by structural invariance throughout your typing context. However, intrinsic verification can be somewhat bothersome in that it can lead to multiple versions of a single plain data type of functional programming when you move to dependent types. For example, for lists there are length indexed lists, provably sorted lists, and so on. With each new variation on a plain data type, programmers must consider whether they want to redo all or some of the functionality for the plain data type, or to reuse this functionality by way of functions converting to and from the variants. For the latter, such conversions typically involve iteratively tearing down the given data structure and rebuilding it into the desired structure, incurring linear time overhead at each conversion. We are going to explore an alternative form of reuse using conversions for lambda-encoded data types in Cedille that takes constant time, that is, zero-cost coercions, which comes from a manuscript by Deal and Stump that precedes their accepted ICFP 18 paper, co-authored with Firsov, entitled Generic Zero-Cost Reuse for Dependent Types. Links to author versions of both of these papers are given in the description. In this video, we will be using church-encoded data with induction manually derived, rather than Cedille's built-in data type system, and manually derived zero-cost reuse instead of the generic results of the published paper. The basic idea is to observe that the information one uses to enrich some plain data type to express some property over it often plays no computational role. That information could be safely erased in many circumstances. For example, length information for lists can be dynamically computed, so length indexed lists do not need to carry around this information explicitly. In Cedille, we can use implicit products to quantify over terms in a proof-relevant fashion. If, in Cedille, we use implicit products for quantifying over the natural number lengths in the definition of length indexed lists, then it turns out that the lambda encodings for length index lists and plain lists are in fact the same after erasure. Let us recall the types of church-encoded lists and length index lists, typically called vectors. The type of church-encoded lists, whose element type is A, is a polymorphic function in X which takes two arguments. One of these is the result that you wish to give in the case that the list is nil. The other of these is a function corresponding to the result you wish to compute if the list is cons. This function takes itself two arguments, a head element A and the previously computed result for the tail, and transforms these into the next result. the type of church-encoded vectors is similar, except instead of being polymorphic in a type, we are now polymorphic in a type family X over natural numbers. This natural number index serves to track the length of the current list. In the nil case, the length is 0. In the cons case, we must work with an arbitrary list whose length is some m, and from this produce a result corresponding to a cons involving that tail, whose length would therefore be the successor of m. As mentioned, notice that the length information in vec is quantified over implicitly in the definition. Because of this, all such length information erases away in the constructors, and we have that the corresponding constructors of each of these data types are equal after erasure. The nil function takes two arguments, n and c, and returns n. And this is the same as the vnil function. Again, because the typing information concerning the length of the list is erased. Similarly for cons and vcons. The method of linear time reuse from vectors to lists involves folding over the given vector, replacing each constructor with the appropriate list constructor. We demonstrate this with a function v2l. For every element type A, for every natural number n, given a vector whose length is that number, return a list. We do this with a fold over vectors, ignoring the natural number corresponding to the length information, and simply returning a list. In the vnil case, we return list nil, and in the vcons case, we ignore the length information and return list cons. The definition erases to the following. An alternative method for constructing lists in constant time has us not rebuilding with list constructors, but with the interpretations of the list constructors that some future fold will use. This is precisely the same technique used for defining constant time addition for church-encoded naturals, and it involves using the definition of list as a polymorphic type and going under the lambdas of that definition. The lists we are using are manually derived inductive lambda encodings defined using dependent intersections. So zero-cost coercions will also be defined in two parts, one for the ordinary church encoding and one for its induction principle. We begin with the church encoding. For every type of elements A, length in vector x's, we must now return a list, a church-encoded list whose elements have type A. But recall, because we are working with church encodings, this is just a polymorphic function. So we abstract over the type and the two arguments it is given. And now, instead of folding over the list constructors, we can fold over these given arguments, which we should interpret as interpretations for the list constructors, or arguments given to some future fold. Give the interpretation for list nil, the interpretation for list cons, folding over the given vector x's. Since fold vec merely applies its vector argument to the given nil and vcons case, turns out that the function v2lc bang erases to and eta contracts to an identity function. We can see this by selecting the span involving the application in Cedille and pressing Ctrl-I in for normalize to see that in fact this entire expression erases to x's applied to ln and lc, which were exactly the variables that we just introduced via lambda abstractions. So if we normalize this expression, it eta contracts to x's. Thus, the entire expression erases to lambda x's. All of the other information is erased. This situation holds when we go on to show that lists built in this way, meaning from the conversion of some vector, satisfy the list inductivity predicate. We do this with a function, v2li bang, for all element types A, for all natural numbers in, for all vectors of A, whose length is in. The list inductivity predicate, list I, holds for those church-encoded lists, which are the image of the conversion function v2lc bang. To give a proof of list I for a particular list, it suffices to assume an arbitrary property over lists x, and two proofs. One, that the property holds for the empty list, and another, that the property holds for the cons of some list on the assumption that that property holds for the tail of that cons list. We can show this by induction over vectors. The first proof we must give is a proof that x holds for the conversion of vector nil. But because this conversion function is identity, and because v nil is equal to nil by definition, this is exactly the same as just giving a proof that x holds for nil. And we have an assumption that satisfies this already. For the cons case, we assume a length and a tail vector And by similar reasoning, know that the proof that we must eventually give is convertible with a proof that X holds for list cons of head and tail. So we use the given assumption LC, which also shows the same result. LC requires a list. We give it such a list that happens to be equal by definition to the assumed tail vector TL. The resulting expression is a function type whose codomain is convertible with the function type we are expected to give, and in general whose type is the same as the type we are expected to give, modulo conversion and erasure. As before, our proof that vectors, when considered as lists, satisfy the list inductivity predicate is also an identity function. We can now put these two functions together, v2lc bang and v2li bang, and produce a zero-cost conversion from vectors to lists. Reuse is also possible in the other direction. Lists can be converted to vectors whose length index is the dynamically computed length of the original list. For every element type A and for every x's list of A, we can produce a church-encoded vector whose length index is the length of the list. Again, we go under the definition of church-encoded vectors. Introducing an arbitrary type family X over natural numbers. And a result value of the type family at 0, and a function producing a result value in the type family at successor m for any natural number m, any head element A, and any result in the type family at m. We can give this definition by induction over lists. In the first case, we must give a proof, or rather I should say, we must give a result value of x over the length of nil, which computes to 0, and that just happens to be the given the given type of the assumption Vn. For the cons case, we are given a list tail and must show that assuming x holds for the length of tail, then x holds for the length of a cons involving that tail. But of course, we know that this computes to the successor of the length of tail. That is precisely what the assumed VC gives us. So we instantiate VC with a length information, length of tail. For the inductivity predicate, we have the function L2VI bang, which takes in an arbitrary element type and an arbitrary list, x's, and proves that the vector inductivity predicate holds for the vector converted from the list x's, whose length is the dynamically computed length of that list. To show the inductivity predicate for vectors, it suffices to assume an arbitrary property over vectors x, two proofs, one that x holds for v nil, one corresponding to the cons case, and now we must show that given these two assumptions, x holds for the vector formed from conversion for the list x's, which we can show by using a proof of induction over lists. As should be expected at this point, the proof we need to give in the nil case is given already by the assumed Vn, as the length of nil is 0, and the conversion of the list nil is definitionally equal to vector nil. For the cons case, we assume a tail and can use the assumed proof VC VC requires a length in one and a vector tail whose length is that given number, and we provide this. The natural number is the length of the tail, and the tail vector is the vector we form from conversion from the list tail. And now we put these two definitions together to get zero-cost reuse from lists to vectors, where the codomain is enriched now with the information of the length of the given list. Notice that there is something of an asymmetry between the two conversion functions. Converting from vectors to lists is lossy, in the sense that the statically available length information is discarded. In order to make full use of reuse, we will want a proof that the length of a list formed from coercing a vector is the same as the length index of the original vector. Call this proof v2l len. Given a vector of length n, we want a proof that the length of the list formed from converting the vector is equal to the length index. Again, we proceed by induction. In the nil case, the vector index is 0, which is precisely what the length of the list nil is. So the equality holds by beta reduction. In the cons case, we have a length in, which is the length of the given tail, a head element, an inductive hypothesis, which says that the length of the tail is equal to the length index of the given vector. We can rewrite by that inductive hypothesis, and then the proof holds by definition. We can now consider a simple example of program reuse from lists to vectors. If we are in a situation where we have the base data type list, a function append_l for appending two lists, and a proof that the length of a list formed from appending two lists is equal to the sum of the lengths of those two lists, then we later find ourselves in need of an append function for vectors, we can reuse this functionality for lists with only constant time overhead. Let's define append v. Given two vectors, return a vector whose length is the sum of the lengths of the given vectors. We do this in three parts. First, we compute the list formed from appending the two vectors after converting these to lists. Then we give a proof that the length of this list, z's, is equal to the sum of the length indices of the vector This can be shown by by using our proof of the desired behavior for append for lists. The length of appending two lists is equal to the sum of the lengths of those lists. Now that we have this, we use our previous lemma that says that the lengths of converted lists, the lengths of lists converted from vectors are equal to the length indices of those vectors. And then we have our proof. Finally, we can put this together by rewriting the type of the expected type for the expression. And converting our given list z's back to a vector. I stress, all of the coercions back and forth incur no serious overhead. We can prove this by showing that append v is equal to append list by definition. We conclude this video with an example of proof reuse. For proofs of equalities, in Cedille, such reuse is even simpler than program reuse, because equality is untyped and over erased terms. Because append vec is definitionally equal to append list, the proof that append list is associative applies directly to append vec modulo some insertion of coercions. Given three natural numbers, m, n, and o, and three vectors whose lengths are respectively m, n, and o, return a proof that append vec is associative. We can do this by appealing to the proof that append for lists is associative, on the lists given by converting the given vectors. Thank you for watching. I hope that you and everyone you know are well during this pandemic. Hope you enjoyed this video, and see you in the next one.